Another type of the data that we have is seasonal data. In seasonal data, we see regular repeating patterns in the time series that we have. These patterns are repeating after the specific time periods. Depending on the type of the change that they have, we divide them into two groups, additive versus multiplicative. The additive seasonal data, they are repeated after a specific time period, but the value that we got for the each period is pretty similar to each other. We don't have much variation in the additive seasonal, but in the multiplicative seasonal effect, we can see that after each time period, the value we observe is increasing. You can see for the first part of this graph, which shows the additive seasonal effect, the seasonality happens, and you can see from time period 2 to time period 6, we can see the data is repeating. Also from data type period 6 to period 10, you can see again we have the repetition of the data. So you can see there is a pattern is happening. So up and down, and this pattern is repeating again. But the value of the in the this part and this part is not different than the value that we got in this part and in this part. So the values are repeated the, in the specific time period. So we call this behavior as an additive seasonal effect. But in the multiplicative, you can see the values in the valley here is increasing. The values are changing. So you can see also in the hill we have increasing values. So we call this kind of behavior as a multiplicative seasonal effect. Once we have this kind of behavior, for each of these models, for each of these behaviors, we have two different forecasting models. For the additive part, we present the forecasting at time period t plus n by two factors. First factor is we represent by ET, we call it as a seasonal expected level. And then we have the second term, which is C at time period t plus n minus p. So we call this as a seasonal effect. And here you can see there's a p. P represent for the distance between the repetition of the seasonal period. So for example, if the data happens annually, the p is 12. But if the data we have is for quarter, for p becomes 4. That means this p depends on the type of the data that we have. Now ET, the expected level, you can assume as a average. For example, here you can represent this one by a linear line, linear value at each time, so the average of this, and then we add a seasonal effect, which is kind of adjustment to the expected level. But the expected level itself is a combination of the real observation minus the seasonal effect at time t minus p and the previous expected level. So each expected level is adjusted based on the previous expected value. Similarly, seasonal effect is adjusted based on the last its previous seasonal time, but there is a p times difference between the ST and the STP. So we adjust this one based on the real observation and the expected level of the current time. So this is a recurring equation between the ET and ST, and we have two parameters, alpha and beta. Both of these parameters are between 0 and 1, and we can use nonlinear optimization to find the value of these parameters. As you notice, we have ET and ST that we at, at some point we have to provide them for the model that we have. So most of the time for time period 1, for the first repetition of the season, for t equal to p, we provide these values. That means for the expected value, we get the average of all the data for a time period 1 to p, and then for the seasonal also we provide this kind of example with this kind of information for the model. So let's have the example and see how we can apply this seasonal additive seasonal effect in the real data. So consider this example that we have annual based. So if we have for year 2011 to 2016, and for each year we have 4 observation. The plot of this graph is represented in this figure. You can see at time period 1 it has a decrease, and then we can observe an increase and then again decrease. So and this pattern is repeating itself. So there is a increase at time period 3, and then decrease. So you can see there is a repeating pattern, and you can see that the time period that the difference between each occurrence, each repeating pattern is 4. For example, you can see from this point up to this point, we can see as one season, so we have 4 observation at each time period, as you can see here also. And then the pattern itself repeats. You see there is this is a starting point on the second time period and the second season, and this is a end of the second season and the starting point on the third season, and so on. So this is pattern is repeating. A lot of the data models are like this. They are a seasonal pattern, and they are additive in terms of the magnitude, so we don't see much deviation from some observed previous pattern. So this is all we can see. Now as we just said, there is two parameters that we have to find those parameters. One of them is alpha, let's say, and the other one is a beta. Now also we have two factors for to find the prediction of the values. One of them is expected level that we represent by ET. Another one is the seasonal effect, which is ST and minus P. So as we just said, for the first period we have to take the average of all the observation. So we can take the average of the first 4 observation, because our seasonal time period is 6. P is equal to 4, so we can take the average of the first 4 observation, and we use for all of the data set for the timeline 1, and then ST plus N minus P, we can get the Y observation minus the ET. So for all of the data set that we have, we can use this. So this becomes, so for the first one becomes 2.5, for the second one becomes minus 17.5, and so on. So for time being, let's assume alpha is 0.5 and the beta is 0.5. So we can, using the MSE we can find those values. And let's have the forecasting. So let's add one more column, the value of the forecasting y hat. So because for the first period we don't have any time period, we don't have any forecasting, let's put them empty. But from now on, we have to use for the expected level and uh, seasonal effect, use the formula, which is the, as we just explained, is expected level is alpha time yt minus stp and plus 1 minus alpha. So let's implement this one. So expected level is alpha times, let's fix this formula, and y time minus stp, which is right now we are at time period 5, and minus 4 becomes 1. So this is the equation that we have to use, plus 1 minus alpha, 1 minus alpha that we have here, and we are using for other the values that we have. So we can fix the cell and multiply by et minus 1. So this is et minus 1 that we have. Now then we can extend this equation for all of the other periods that we have. So we copy and paste as a equation. Now let's work on the stp plus n minus p. So again, let's back to the equation. St is beta times yt minus et plus 1 beta times st minus p. So beta times yt minus et plus 1 minus beta times stp, which is this value. Sorry, we have to start from the first period, which is 1 minus beta beta times yt minus et times plus 1 minus beta times st minus p. So this is the equation that we have. So we can use this stp for the rest of the time periods that we have. So this becomes this way. Now the forecasting becomes equal to the value that we have for period t minus 1 plus stp plus n minus 1. So this value, and then we use for all of the times that we have, so we can copy as an equation. Now let's get the MSE, which is MSE is, we can use the sum x my2 of the value that we forecasted and the value that we have already observed. So this provides this value. We can divide by the number of the items observation that we have, but let's divide by number of the observations, so be exact. So this, we can use the count function. So this is the value that we got for the MSE. Now let's use solver. So let's implement this solver, and our objective function is this cell, and the type of the objective function is minimization. Then these are the decision variables that we have, and the value of this decision variable should be between 0 and 1. So let's add these constraints. And then because we are dealing with the nonlinear optimization, we put select the GRG nonlinear optimization, and then we solve this problem. So you can see we got the value of the alpha 0.7, uh, 0.57 for the alpha, and the beta equal to 0.276. So these are the forecasting that we have, and then we can use this forecasting for the next period. So for the 2017, our forecast for each of the observation for each of the time periods is as follow. So we will get the 362 for the for the time period 1 is this value plus the seasonal effect of the time period 1. For the second time period is this value plus the seasonal effect of this value, as the equation says, and for this value we have the value of this the ET and this value, and then for the last one we have seasonal effect plus the expected level. So this is the value that we have. Now let's compare the forecasted model with what we got with for the forecasting. So let's add the data, and so these are the observation that we have. So you can see we are pretty much close to the real data that we have. So this purple line is forecasted, and the blue one is a real observation, and our errors MSE is 304, which is pretty good. You can see the data set that our forecasting model is closely follows the behavior of the original data. So that's a pretty good observation. Also, we can get the forecast for the next period. So that's a very interesting use of this model. So for the forecasting of the time periods 25 to 28, using the time period 24, we have to follow this equation. That's once for the 25, we have to use expected level of the 25 plus seasonal effect of the period 21 that we used, and we got this value. Also for 26, we have to use the expected level at time period 24 plus the seasonal effect of time period 22, and so on. So this is a way that we can use the expected level and seasonal level. So basically expected level is a constant, and then we add a seasonal effect to the data, which represent the value that we have. So this is a way that we work in the additive seasonal. Now let's move to the stationary data with the multiplicative seasonal effect. The way that we work in this model is exactly the same as the additive, except that For the multiplicative, this plus sign that we had for the additive becomes multiplicative, and the minus sign becomes division that you can see here. Again, we are using two parameters, alpha and beta, and both of these parameters are in the range. Everything is similar to the additive except that these signs are changing. So if we compare the multiplicative versus the additive, you can see that in the multiplicative we have multiplication sign here, and here we have the additive sign. But for the in the multiplicative we have a divide here, but we have a subtraction here. So let's do the example that we had for the additive and see the value that we can get for this value. So let's use ET and ST. So again, for the first period that we have to use the average. So it becomes average of the first observation that we have for year 1, because here P is the P is 4, so we have to use this average. And the seasonal effect is yi, real observation over the ET. And again, we don't have a forecast for this one, so all of the values are, we don't have any observation. And then the similar way we have to define the alpha and beta. So let's define the alpha and beta, and as well as the MSE. So let's define alpha 0.5 and beta 0.5. Similar to additive model, we have alpha times the real observation divided by the STP, which is a P time period back, plus 1 minus alpha times the previous ET that we have. So this is the value. So we can use this value for all of the rest of the observation that we have. Let's copy and copy the equation. Now for the ST we have beta times real observation YT over the ET plus 1 minus beta times STP1. So STP minus P, so we are using P times behind the current observation. Beta times, all right, so, and then we use this equation for all of the rest of the equation that we have. Now the forecasting is this value multiplied by this value. So again, remember here we had a summation, but here we have a multiplication. So this is a multiplication that we get. And then for the forecasting part, we use the last observation multiplied by P times behind of the current time that we have, and we use the last period, last observation for all of the observation that we have. So this becomes the forecasting. And if you compare the values, you can see there is not much difference between these two models for this database, the type of the data that we have. Let's plot and see how we are doing in the original, comparing the original data and the one that we got from the multiplicative forecasting. So if we plot that, you can see we are doing pretty much similar, even though we have not optimized the alpha and beta yet. So let's do the optimization. So sum x my2, that gets the difference between the square root of the difference between two vectors that we have. So this is the first vector and this is the second vector that we have, and then let's divide by the number of the observation count, so becomes this value, and the objective function is this, and the decision variables are this, and they are less than 1 and they are positive. So this is a setup, and GRG nonlinear, and you can see the error is pretty much 0. That's perfectly matching the data, and you can see the green line, which is the multiplicative part, is exactly matching the data even better than the additive. So here we can use a multiplicative part, and we can make sure, we can be pretty sure that the value that we are getting as a forecasting is better. And you can compare the forecasting values, they are pretty in the same value, same range. So we can use either way, but it seems that multiplicative, because it's doing good in the observation that we have in terms of the MSE, we can rely on the forecasting based on the multiplicative. So this is the end of the lecture. Thank you.